Okay, so quite a lot to go through with this video. Hopefully I'll get it done. As I mentioned before, sound waves travel longitudinally. The medium through which it travels is in the same directions parallel to the energy of the wave. And so sound can travel through any medium as long as there is one, air, water, etc. But it has to have something like that. A speed of sound through air at 0 degrees Celsius, so 1 atmosphere of pressure, standard temperature and pressure, is 331 meters per second, and it increases about 0.6 meters per second for each degree Celsius in temperature. So at 20 degrees Celsius, if you were to calculate that, you get 343 meters per second, which is often what is used in our problems. So generally we'll put it at 20 degrees. If for some reason it doesn't specify, you just kind of assume it's about 20 degrees. Right about now we have thunderstorms starting, and thunder is heard much after lightning is seen because of course light travels much faster than sound. Light travels at 3 times 10 to the 8th meters per second, and sound is only 343. So it would take the sound of thunder about 5 seconds to travel a mile. So if thunder is heard 6 seconds after we see the lightning, then you can think around lightning struck around 1.2 miles away. All right, and so as it gets closer, that time, it goes shorter and shorter time period between them. Speed of sound through helium, water, iron. If you've ever seen those old westerns where someone puts their ear to a railroad track, you can hear that vibration from a long ways away. So sound travels slowest in gases, fastest in liquids, and faster in liquids, and fastest in solids. All right, some other things that we can calculate with sound is loudness. And loudness refers to the pressure amplitude of the sound wave. A typical conversation has a sound pressure around 0.003 pascals. It's a little louder now with social distancing. Intensity is the rate at which energy is carried across a unit area by a sound wave. So if you remember with power and watts, how many units that encompasses, this is actually watts over an area of meters squared. As the amplitude increases, the intensity increases, the loudness increases. People can detect intensities of around 10 to the negative 12 watts per meter squared, up to about 1 watt per meter squared. And as we get older, that's harder for us to detect. And you might have there was this ringtone that you can use before texting. There was still some cell phones, but not texting. Kids would set the ringtones to a pitch that most of the teachers, after around 25 or 26 years old, you can't hear that pitch. It's too high. The intensity level is known as a decibel, and decibels are equal to 10 times the log of intensity over a base intensity, where the intensity level of sound being measured and it's whatever sound you're measuring, and the reference level there is going to be the threshold of hearing, which is 1 times 10 to the negative 12. So if a sound's intensity is that, then we can calculate. We're going to put this in for this. When you're calculating, by the way, I would go 1 EE negative 10. Just put the 1, put the EE in negative 10. Divided by 1 EE negative 12, we're going to get 10 times log of 10 to the second, which is going to be 20 decibels. And notice that 30 decibels is 10 times more intense than 20. Because we are using the base log, we're looking at, or 10 log, we're looking at 10 times more intense for every 10 decibels increased. To calculate the intensity, we're going to use this formula here, and we're going to use power over 4 pi times the area, the distance from the sound source, squared. So if we were to find out the intensity of the sound produced by like a band like Aerosmith playing Dream On, I guess they're getting a little old, I probably should change to a different band. If you're 35 meters away from a speaker and the music is playing at 120 decibels, what is the sound power? And you're going to find out that that's going to do some damage to your hearing, so it's probably not such a great idea. All right, so we have 120 decibels. We know that the decibel formula can be found by finding the intensity over the threshold intensity, which is the threshold of hearing. And so what we want to do is calculate that intensity. And then what we want to say is, all right, well, that intensity is going to equal our power over 4 times pi, and we're 35 meters away. And so our power then is going to equal that times 1, which is going to be 1.54 times 10 to the 4th. And now this is going to be watts, like power is, okay? Because the meters squared here will, that's meters, and the meters squared will cancel. Okay, whoops. We're going to look at Doppler in just a second here. Okay, so talking about that pitch again, frequency and pitch are directly related. The human ear responds to frequencies around the range of 20 hertz up to about 20,000 hertz. Old people can hear usually up to about 10,000 hertz. Chemotherapy can cause a higher pitch hearing loss too. My husband went through chemotherapy, a year of it, and lost a lot of that higher pitch. If he wants to go bird watching, which he loves to do, he has to get this little machine we got was $600, and it allows him to, it's like a hearing aid kind of, but allows to hear those higher pitches. Ultrasonic is above 20,000 hertz. Dogs can hear up to 50,000 hertz, and bats up to 100,000 hertz. Infrasonic is below 20 hertz. Thunder, volcanoes, vibrating heavy machinery. Sometimes that actually can set up resonance and internal organs, causing damage, but that's another whole story. All right, so looking at the Doppler effect here, we know what the Doppler effect is. The pitch changes if the source or the listener is moving. Now, we normally think about the source moving, not the listener. So we have like a police car, an ambulance, a fire truck coming toward us and then moving away from us. So when a source of sound is moving toward an observer, the pitch is higher because those sound waves are piling up. So if you're just standing here, or the fire truck, I'm not even going to try to draw a good fire truck here, is just standing, not moving, the sound waves are evenly spaced. However, if you're standing here and the fire truck is coming toward you, those waves are going to pile up, and they're actually going to spread out behind you so that you can see, and as it goes past you, you're going to experience now, as the truck's moving away from you, you're going to experience, I'm going to try to draw the truck. It's gone off the screen. The waves are coming less and less at you. Okay, the formulas for calculating this, and I don't think I do any observer moving. If you do, it changes things, but if it's the source that's moving and you're standing still, what we have as a formula here is what you hear. Let's call it you rather than the listener. Let's talk about you. You're the listener. So this is what you hear. And this is the actual frequency of the sound. Okay. And so then what you want to do is to calculate this. You've got V sub S is the speed of the sound source. So the speed of the fire truck, wherever, okay? And this is the speed of sound. And at 20 degrees, we're going to use 343 meters per second at 20 degrees, okay? Now, this is if it's moving away from you, and this is if it's moving toward you. If it's moving toward you, you're going to use this formula. If it's moving away from you, you're going to use this formula. Again, you could do it if you were the one, I don't know, running toward a fire truck. I don't know. I don't think I have that on the formula sheets or the worksheets. Okay, so let's just take a look at a couple of examples here. Police car, car, moving away from you at 30 meters per second and toward another person with a siren blasting at 1440 hertz. What frequency do you hear? What does the other person hear? So probably good if the police car is moving away from you and towards somebody else. Okay, so what do you hear? That's F prime. We're going to go frequency. So the frequency of the sound is 1440. And definitely take a second to plug this in and just make sure that you're understanding what's happening. Okay. So popping that all in, you should get 1,325 hertz. Okay. The other person is going to use this one. And so that person, as it's coming toward, is going to be 1440. Oh, I already did that. Oh, well. And again, plug that in, and what you should get is 1,577 hertz. Okay, the pitch is going to be higher. Okay, a couple of things. Light also exhibits Doppler effect. If you ever decide to study astrophysics, that is a very useful tool for people, astrophysicists, to understand what's going on in the universe. That's how basic idea of why they know that the universe is expanding since the Big Bang time is because of the Doppler effect. Police radar also uses Doppler effect and electromagnetic radiation to measure the speed of approaching cars. And I can stop you for speeding. All right, one last thing I want to do before the time runs out on this video is to talk about shock waves and sonic booms. And I did put the link there, and I think on the next slide the video is actually embedded. Mach 2 means the object is moving twice the speed of sound. What's happening with a sonic boom is that the source is chasing the sound waves. So the sound waves are moving out in front of it. Picture that beautiful picture I did with the fire truck. The waves coming out in front of it. And if you're in front of the fire truck and it's coming towards you, those waves are piling up. Now, the fire truck doesn't go supersonic. That would be bad. But certain jets can do that. And so the source is chasing the sound waves moving out in front of it. And they're just physically piling up in front and overlapping constructively. And the plane actually has to break through that barrier of piled up sound waves and the molecules in the medium, and requires an extra thrust of power to break that barrier. And it's broken repeatedly as those waves pile up again and again and again. So definitely watch that video. Oh geez, last video or last slide I wanted to show you. Ultrasound, to talk about that a little bit. Sonar to locate underwater objects. The transmitter sends out a sound pulse and a detector receives its reflection, echolocation. And you can calculate the distance of that object. I don't know the details of that, but supposedly bats could do that as well. Exploring for oil. Okay. Detecting abnormalities in ultrasound. Those have really increased in what they can do in the last, say, 20 years. It's kind of amazing what they can, the kind of picture they can form of a fetus. All right, so that is it for this chapter.